Yeah, thanks. So, yeah, I'm a PhD student with Jens Eisert at the FU Berlin, and today have the pleasure to tell you about quantum metrology in the finite sample regime, as you just said. And this talk is based on the preprint of the same name that we put out last year with my amazing collaborators, Sumit, Daniel, Jens, and Philippe. And I also get started with like a short introduction of what quantum metrology is. And if you ask Google, it will tell you that it is the scientific study of measurement. And as a particular example of this very physicsy thing, so it's really at the heart of what physicists do in labs, you know, that's something that people at QRP usually are not so familiar with. But one particular example that should be familiar is the idea of phase estimation. So you have an ensemble of spins, you initialize them in some state, and then everyone separately undergoes a phase shift, but it's always the same phase, t. And the catch is that t is unknown. And we are kind of there to design a protocol, so find a good initial state and find a good measurement at the end to extract what the value of this parameter t, this phase, actually is. And in practical applications, there are actually limitations of this. So first of all, nowadays we can usually only manipulate a low number of physical systems actually pretty well. And we also have sometimes a slow operation speed depending on the platform. For example, neutral atoms or ions, they're not terribly fast. And we also often have the problem that the system parameters, they undergo some inherent drift. So they change over time, and after a certain characteristic time of the drift, we kind of have to recalibrate our whole system. Yeah. So basically what this means is that the resources that we have available for quantum metrology are actually usually limited, and we cannot just assume that we always have like an asymptotically large number of systems or copies to work with. And this is how I motivate that practical metrology actually happens in the so-called finite sample regime, which is just the regime I was talking about. Like, we don't have infinite resources. And you know, on the top left, I wrote that the goal is to devise a very good protocol for estimating this unknown phase. And you can always keep this phase estimation example at the back of your mind during the talk. Okay, so basically, how have people been going about this whole finding a good protocol thing? And for this, we need some sort of theoretical abstraction. And in this talk, I will put an emphasis on the following. So we assume we have given a parametrized set of quantum states, rows of t. So like, for example, you fixed some initial state for your phase estimation, and then it underwent an unknown phase. And depending on the value of the unknown phase, it's a different state. And this is like, can be seen as an instance of a parametrized set of states. And then basically what you are left to do is to design a measurement and somehow find a post-processing of the measurement outcomes into predictions of the actual value of the parameter. And all of this, like measuring and post-processing, can be absorbed into a POVM. And the values t hat that index the POVM are all the possible predictions we could have. Yeah. So this is kind of the mathematical framework. And if we want to optimize, we need a kind of like a figure of merit to optimize for. And traditionally, people have been looking at the mean squared error of the estimate. And if the estimate is exact in expectation, then this is nothing else but the variance of the estimate. And for this, we have this very nice and elegant tool, which is the Kramer-Rao bound, which just says that there is actually a fundamental lower bound on the achievable variance given by the inverse of this quantum Fish information, this F quantity here. And this quantum Fish information, it measures the distinguishability of nearby states, so states around rows of t for a fixed value of t. And you can see it mathematically speaking here. So if you look at the fidelity of row of t and then look at a neighboring state for a small perturbation tau, the first non-trivial order, the second order, will be proportional to the quantum Fish information. So that is kind of like an intuitive definition, how it measures the distinguishability of nearby states. Okay, so, and then what about this finite sample regime that I told you about, right? So basically what you can say is that obviously this Kramer-Rao bound, it still constrains the precision even if I only have few copies available. So basically it's kind of like a necessary condition to have large Fisher information, but it can also be that it's overly optimistic. And this means that if I only optimize for large Fisher information in my probe state, so to speak, or in my measurement, then this can actually lead to a poor finite sample performance. And we will see an example of this later in the talk. Yeah. Okay, so this is the traditional approach, and I just want to emphasize that it's really nice because this whole Cramer-Auer-bound business, because we can actually saturate it, means that in order to understand how well a metrology scheme is performing asymptotically, we only have to calculate one number. But this also means that usually all people are doing is calculate one number, and I think if we want to understand the finite sample regime, we have to go a little bit deeper. And so how are we going about this? Basically, we say we want to have a figure of merit, which is like much more compatible to this like idea of having like finite resources where we don't need like asymptotically many. And one way to go about this is to do the following. So we first define an estimation tolerance, a value of delta that we actually want to achieve. So we want to say maybe delta is 0.01, and this means I want to estimate the phase, the value of t, up to a precision of 0.01. And then we can ask, okay, but what is the probability of our procedure that we came up with actually outputting such a good estimate? So basically what we care about is a success probability of quantum metrology. And if I say success probability, yeah, you might ask probability with respect to what? Yeah, so we need a way to assign probabilities to this. And basically this means we need a way to model the idea of the parameter is unknown to us. So that's what we are doing on the next slide. Basically, we just take the same setup as we had before, and then we have, in our paper, we look at two possibilities. So the first thing is, you might have already have some idea of what the value of the parameter actually is. Maybe you did some experiments before, maybe you just know your system very well. And this you can all model with like a Bayesian prior distribution for the value of the parameter. And this, together with this idea from before, gives us this definition of a Bayesian success probability. So basically, to plug this math formula apart, here at the end, we see, assume the ground truth, so the actual value of the parameter was t, and we measure our POVM Q, and then all the good values, the ones that we say are correct because they are within the tolerance, are just like, you obtain it by integrating this up. Yeah, and so this whole black block here is just like the success probability conditioned on the ground truth actually being t, and then to get the Bayesian formula, we just take an expectation over the prior distribution. This is one way to define a figure of merit for this. The other way is, what if you ask yourself, okay, I do not want to make Bayesian assumptions. So I reject Bayesianism. I talked to a cubist once. I never want to do it again, something like this, right? And then you say, okay, can we do something that does not rely on priors, that does not rely on any kind of outside information that I have to put in, and that is actually also possible. So what we can also do is we model our system with an adversary. Yeah, so you kind of design your protocol, and then somebody is coming, the adversary is picking the value of the ground truth, t, that for which your protocol works the least well. And then instead of the expectation value over the prior, you just obtain the minimum. But the cool thing with this like adversarial quantity that we call minimax success probability, to be consistent with the rest of statistics, is that it can actually be guaranteed against any prior distribution that your parameter could have. So it's like this eta bar here is a lower bound for all the possible etas for all prior distributions. So this is kind of nice because it's really like encoding this idea that you really have no knowledge about the parameter whatsoever in a way that is just better than just forming, for example, a uniform prior, which also is some kind of assumption. Okay. So this is now the definition of these like figures of merit that we want to use in a single shot case. And I, for the rest of the talk, will focus on the miniwax one just because the results are usually easier to show. And I motivated this metrology at the start with this goal to find like an optimal protocol for this. And we can actually also just like write this up just as a math formula again. And you see, I now just put a star on this eta bar and say I want just like the largest success probability that could be achieved with a POVM, with a particular sort of measurement. So this is kind of the design on a mathematical level of an optimal measurement. And In our paper, we show that this optimization constitutes a so-called semi-infinite program. And for the connoisseurs in the audience, it's just like a continuous version of a semi-definite program. So it's a nice convex program, and it gives us a lot of nice structure to work with. And I showed you the thing here for parameterized states, but it also generalizes to protocols that involve quantum channels, like, for example, adaptive protocols like the one we saw in the previous talk. Okay, so we can also optimize in that case. And because I told you that these are still like the figures of merit, so to speak. And in this traditional approach to quantum metrology, we had a figure of merit, which is like the variance or the mean squared error. And we had like a very good fundamental lower bound, which is the Kramer-Rao bound with the inverse Fisher information. And we want to have something on a similar level of fundamentality for the success probability. And what we do here is we can connect it actually to hypothesis testing to also get like a fundamental bound. And the motivation is that we expect that if we want to estimate the parameter to precision delta, but if states that are only delta apart in the parameter are hard to distinguish, that sensing the parameter should also be hard. And we kind of make this intuition formal by performing a reduction from quantum metrology to quantum multi-hypothesis testing. In our case, it's a metric case. So basically the task, somebody is giving you states, and your task is to design a measurement that tells apart these states. And the proof is actually quite simple, so I can actually show it to you. Basically, you imagine you have a parameterized set of states, and now you choose like 3 of them, yeah, at 3 different values of the parameter. And now you say, okay, but what is the probability of me hypothesis testing these 3 parameters? Yeah, so you want to design a hypothesis testing POVM for these 3 quantum states. And basically, if we just like remember that this was like a metrology problem in the first place, we can actually solve the hypothesis testing task using the metrology protocol by just like measuring the literal metrology protocol and then just predicting, as I did here with these green dots, the closest state in parameter. And because we have these like tolerance regions delta, and I chose these values here such that they don't touch, we actually know that the probability that this process is giving us the correct output has to be at least this minimax success probability eta bar. And now, because we can use the metrology protocol to solve the multi-hypothesis testing task, we just obtained a theorem that if the hypothesis testing task is hard, then the metrology task also has to be hard. And this whole reduction business also works, again, in the case of like parameterized channels and so on, different access models. And it allows us to develop a lot of these results that we have in our paper. And also, for example, analyze the asymptotic rate. So basically, how quickly for a fixed tolerance, the success probability achieves 1 if I get many copies, to also get an understanding of how the asymptotics look like. So it's just like the really fundamental tool that we develop. And basically, to recap, I showed you at the beginning this success probability, this minimax success probability, and which is literally the answer to the question, what is the probability of obtaining an estimate within a fixed tolerance? But often, metrology people are interested in something else, which is kind of like, okay, I want to have a sort of a standard deviation, some measure of like confidence or how large the deviation of the parameter actually is. And this we can obtain as by reversing the question. So what is the smallest tolerance that still guarantees a fixed success probability? So it's literally the inverse function, yeah, of the above. And it's much more in line with what metrology people usually look at. So it's like a standard deviation, at least unit-wise. And there's then a third thing that you can look at, which is the sample complexity, which you obtain by saying, okay, I want to have both a fixed success probability and a fixed tolerance. And then the only thing that you can still manipulate is the number of copies of your system. Yeah? And all of these 3 things are important quantities if you look at single-shot quantum metrology. And the thing is that all of them are also interesting in different contexts. For example, state tomography is also a form of metrology at the end of the day. And there, what people usually care about are sample complexities. In metrology and sensing, people usually care about these estimation tolerances, and quantum info-minded people, they usually care about the success probability. So all of them are very important. And I want to conclude the talk or the technical part by showing you a bound on this like second quantity, the tolerance, because we recall that at the beginning we said this Kramer-Rao bound, it still bounds the precision even in the finite sample regime. So how does this reflect in our setting? Yeah. So basically, we recall that this Kramer-Rao bound looked like this, and I now just like took the square root to have the right units. Yeah. And we expect that we can have a bound that also kind of looks like this in a certain way. And I will now show you the bound, and then I will explain it to you. So basically, we see that this like minimax tolerance has a lower bound, now given by the minimal Fisher information. So this is kind of due to the worst case nature of this minimax success probability, because it should really work on the whole parameter range that is allowed, for example, for a phase 0 to 2 pi. And then we also get this factor here, this log 1 over 1 minus eta bar. So eta bar is the desired success probability. So this is the inverse probability of failure. And the log of the inverse failure probability is something you should be familiar with, because this is like the generic scaling that you always need if you do statistics. So this is also expected. And then we have this innocent looking factor Q here. And this quantifies how close we are in a certain sense to the asymptotic limit. And I mean, I cannot show you the formula here because like that would take a long time, yeah. But in the IRD case, where we just like get n copies, it would scale as order 1 over square root of n, yeah. Okay, so we have something that resembles the Kramer-Rao bound, which is nice. Now, I want to come back to this phase estimation example that we had at the beginning of this talk and how to do it in an optimal way. So we recall what we understood as phase estimation. So we have these like ensemble of spins undergoing this local evolution. And now what we do is in our paper, we show that a pretty good measurement. So basically choosing the POVM effects proportional to the actual state projectors is optimal in this case. Then this allows us to compute a closed form solution for the minimax success probability. And because we have this closed form solution for the minimax success probability, we can actually do numerics and compute these quantities for up to 10,000 spins. Yeah. Normally, if you would just like solve the convex program, this would be much, much harder. Yeah, because we can have these like, we know the optimal measurement at the end, we can now optimize over the input state. So we can really understand how different probes for quantum metrology behave. And this now gives us 2 plots. I know people love plots, yeah. Okay, so basically what do we have here? So on top we see what the desired probability of success is. On the left 90%, on the right 99.9%. And basically the right one is much harder. Yeah, so we want to be much more sure about our estimate. And on the y-axis we have this achievable minimax tolerance, and it's a log-log plot. So straight lines are power laws. Okay, so what do we see here? Basically, we first see this green line. This corresponds to, I just like take a plus state on every qubit, no entanglement, and or on any spin, and this gives us the standard quantum limit. Then we have the optimal thing that falls out of the optimization. It actually achieves this Heisenberg limit, 1 over n. So this is also nice because we see like the hallmarks that any good theory of quantum metrology should have, also in these quantities that we defined. So it's a good sanity check. And then we also have this orange guy here. And this is the so-called Holland-Burnett state. This is a uniform superposition of all eigenstates of the joint system Hamiltonian. And I can tell you that the Fisher information of the state is more or less the same as the one of the optimal state. Yeah? And the Fisher information is also independent of the success probability. You know, it doesn't really figure in there at all. And we see that this Holland-Burnett state, it also achieves the Heisenberg limit. Yeah, but for the right plot, you have to believe me a little bit, but it does. Yeah, and now the interesting part here is that, you know, it has the same Fisher information as the optimal state, but now we have this performance gap that opens depending on the desired success probability. And this is something you cannot predict by looking at the quantum Fisher information alone, because it's the same on both plots. Yeah, so there really is a state which asymptotically has the Heisenberg limit. It has very high Fisher information, but it can still perform very poorly if you have a desire for a high success probability. And this is something which shows that there is a gap between like this finite sample theory and the asymptotic theory of quantum metrology. Okay, so now as a summary of the talk. Basically, we argued that understanding quantum metrology in this finite sample regime, which is practically important, requires us to have like tools beyond the Cramer-Rao bound. And we also changed our perspective from quantifying these variances to success probabilities to remedy this fact. And then this allowed us to rigorously study this finite sample regime and unearth this like relatively fundamental connection to quantum hypothesis testing. And with that, we opened up many exciting directions, I think, in a field that was, by many people, considered relatively, solved. All the fundamental work has been done in the 70s, 80s, 90s, and now there's nothing more to do. But no, in the finite setting, everything is completely wide open. So for example, we have a lot of questions here. So find protocols that have good out-of-the-box guarantees, see how noise and error correction fit in this picture, and also understand how much we can actually gain in the finite sample regime with adaptive processing. And I think that's also a very important one because there I really expect that there will be like a noticeable gap. So what we can actually practically do. And with that, I want to invite you to explore or join us in exploring new exciting directions in quantum metrology. And this is kind of a good chance for you to apply kind of hardcore theory, but with like a practical application in mind. And with that, I would like to thank you for your attention. And here is also a link for a PDF for the slides. Thanks.
Questions? I guess I can start with a small question. So can you extend this to a multi-parameter estimation? I guess you talked about single parameter.
Relatively straightforwardly.
Is it in the paper? Or?
Yes.
Hey, thanks for a really cool talk. Could you comment on bias here in the estimators? It's kind of contained in this success probability, but typically, right, at least in the asymptotic case, right, for the Cramer-Rao bound to hold, you need to be in this asymptotic unbiased regime, and yet you kind of still said, okay, this still applies in this case. So just could you comment on that one?
So let's say like this. I mean, yes, for the vanilla Cramer-Rao bound to apply, you need an unbiased estimator. That's what I kind of wanted to sweep under the rug with this idea that, they have to be exact in expectation. But in principle, there also exist variants of the Cramer-Rao bound that incorporate the bias. So also, for example, in the original work by Hellstrom, like 6701, is like with bias. So I mean, bias is not so problematic, I would say. And I mean, for us, it's just like, it doesn't matter.
I have a question which is maybe a bit naive. So you had this different constants in the scaling, but very much with some different states. And is it possible that you can bridge the gap between those things by some usual classical tricks for post-processing, like, I don't know, taking the one like asymptotically optimal but poor constant state and just use some median of means tricks to boost the success probability to match the other one that the optimal thing was in your?
I would say no. The thing is, like, these median of means tricks, I mean, they will at the end of the day only give you the same 1 over square root of n scaling anyway. So if you want to have something which is Heisenberg limited, I think that should not help too much. I mean, but I didn't look into it super deeply. So, I mean, there might be something, but I would be a little bit doubtful because, I mean, if we say we optimize over the POVM, we implicitly already optimize over the post-processing, and that also includes things like median of means. So, because median of means is just like a post-processing.
Yeah, for the optimal one, I understand. But if you start with this other state, which was not optimal, but
no. I mean, we always have the optimal measurement and post-processing at the end, and we at the end in this plot we only optimize over the input to the phase estimation. So like this whole optimization and how you interpret the measurement into like parameter estimates is already been taken care of.
Okay, thank you.
Hello. So if you went from a parameter estimation from a single copy to state estimation with a single copy, I mean, of course, I mean, there are results that are known that if you use the estimation fidelity, so the average fidelity, if you, let's say you have a qubit, you integrate over the Bloch sphere of the pure states, then it turns out that certain measurements are optimal, or that certain estimates are optimal. Basically, they correspond to the eigenstates of the observable that you measure, or to the if you have, I mean, first of all, the POVM should be a PVM, and then you guess the thing. How does that compare? So if you take your optimal estimate, which is this minimax thing, and you would go to state estimation, do you have an idea what you would find out, what the optimal estimate would be from a single copy?
So I think like several comments. So first of all, this is a can of worms. So we could talk about this for an hour probably, how this stuff extends to state tomography. Then a comment. So the thing is that this minimax success probability that we kind of use here, if you generalize this to state estimation with some sort of distance measure between the states, could be fidelity, then this is already what people look at. Yeah, so I mean, they look at the sample complexity version of this, but it's derived from this like minimax quantity. So this is already what people study, basically. And I mean, the details of your question, I mean, I just cannot answer because, I mean, it's relatively specific and I just haven't thought about it.
Yeah, so let's proceed with questions, but people who have to go to the other sessions, feel free to,
Thanks for the talk. I think it's really cool work in a really cool direction for metrology. I was curious, is there any natural compromise between this Bayesian approach and the minimax one? So like, as an extreme example, maybe I'm pretty sure that my parameters is in some like interval, and then I could just minimax over the interval. But is there like a continuous version of this sort of?
I mean, you can also, so the thing is that the regular setting where you usually look at this Kramer-Raubaum is local estimation, where you say, I actually have a very good idea where the parameter is, and actually I know it, yeah, kind of, and I only want to suppress small like deviations from that, and that you could model, for example, by a very sharp prior. Yeah, and people have been looking a lot into this Bayesian stuff also to understand like if there's a gap in the Heisenberg limit, for example. There's a good paper by Rafał, Demkowicz, Dobroshansky, and these people on this, where you see that there's essentially a gap of pi, yeah, in the two limits that you can get. And I mean, we didn't look so much into this and how you can transition from like this minimax approach to let's say more Bayesian or more local approach. But basically, if you don't mind going to the asymptotic, I think you can always spend like a sublinear amount of your samples to just like get a good idea where your parameter actually is, and then do the local estimation thing. But I mean, this is really only like a good argument if you want to go asymptotic, and which we don't want to do. Mm-hmm. But I mean, I think there's a lot of work to be done in understanding this, and also maybe analyzing adaptive protocols where you say, okay, I first do the minimax thing, then I get some samples, then I make a Bayesian prior to the optimal Bayesian thing for that prior, and then perform a loop, and I get more and more refined estimates. Mm-hmm. I think that would be like a good strategy, but somebody has to work it out.
Cool, thank you.
Any more questions?
Okay, thanks for the nice talk. I was just wondering, like, like, can you go back to the slides of the numerics? So, like here, I don't understand one thing. Like, does this HB really achieve the Heisenberg limit in the standard sense?
Okay, well, then the question is what the standard sense means. I mean, the fish information is proportional to order like n square or n, depending on if you take the square root or not.
So if you take the variance as an, if you take the variance as a figure of merits, and I guess the optimal state is this sign-shaped clock state.
Yeah,
and
it's the GSS state you mean, or?
Does it really? Okay, if I remember correctly, this achieved the standard quantum limit in this.
You mean this Holland-Burnett state here?
Yes.
So I mean, let's say our numerics also strongly indicated, for example, in this left plot, it achieves this. No, I mean, I would say it achieves it, but we can talk about this maybe in detail later, because there are some publications where for other figures of merit, like I think mutual information, this Holland-Burnett state is the actual optimal probe state for phase estimation, for example. Yeah.
Okay, thanks.
Yeah. By the way, if you're interested in this, you can also talk to this guy. Yeah.
Yeah, well, let's thank Johannes again.